A Petrophysics Daily, your daily petrophysics guide.
Glad to be here, as always.
Yeah, welcome. So imagine you're sitting there, right, staring at your computer screen. You're looking at this jagged line on a well log,
hmm
and you know that a $10 million drilling decision rests entirely on how you interpret that one specific line.
Yeah, no pressure, right.
Right. I mean, you've got massive capital, a super complex drilling operation, months of planning, and it's all bottlenecked right at your desk.
It's a terrifying position if you don't have the right foundation.
Exactly. So today we're doing a deep dive into issue 0006 of Field Guide to the Subsurface. We really want to understand why taking that single jagged line at face value is just a devastating trap.
Oh, absolutely. It's a huge trap.
Our mission today is to unpack the beginner petrophysics workflow. This is based on Chapter 1 of Elsevier's 2016 text, Petrophysics. We're getting into how you actually protect the quality of your interpretations when the stakes are just that high.
Yeah, because, well, the subsurface is entirely unforgiving of bad assumptions. It just is.
It really doesn't care what your software model says.
Exactly. When you're conducting a manual technical review of this kind of data, the core philosophy you got to adopt is that rocks tell a geological story, and you cannot skip to the final chapter.
Right.
You know, the environment that rock was born into, the structural forces it's endured over millions of years, the chemical alterations, all of that dictates the actual numbers you eventually see on your screen.
So it's not just random data.
Not at all. The workflow we're dissecting today, it forces you to let that geological narrative unfold in a very specific sequence. You can't just, extract a mathematical value from a software program and call it reality.
Yeah, and the sources are incredibly strict about this sequential order, aren't they?
Very strict.
Like the absolute golden rule here is that a disciplined workflow is your only shield against total interpretation collapse. You got to start with the rock context.
Always start with the rock.
Right. And once the rock is defined, then you move to the physical properties, then you check the fluids, then the downhole measurements, and finally your interpretation checks.
Because bypassing that exact sequence is, well, it's how catastrophic financial mistakes happen in this industry. If you jump straight to some random curve on a log to make a sweeping conclusion about, say, reservoir volume, you are no longer interpreting a physical reservoir.
What are you doing then?
You're interpreting a mathematical artifact. I mean, a log response is really just a secondary echo of the rock's physical architecture. If you don't define the architecture first, the echo means literally nothing.
Okay, let's unpack this. Because that idea, the rock's architecture giving meaning to the data, that's basically the linchpin of this entire workflow.
It really is.
Jumping straight to a conclusion from a single data curve, it's kind of like trying to review a movie by only looking at its opening weekend box office revenue. But you don't know the genre.
Oh, that's a great way to put it.
Right. Like if a movie makes $50 million, you might just assume, oh, it's a massive action-packed blockbuster.
Sure, 50 million sounds like a hit.
But what if it's an independent 2-hour documentary? The revenue number alone lacks all physical context.
Exactly.
You need to know the genre to understand whether that $50 million represents, a catastrophic failure for a superhero franchise or just an unprecedented, record-breaking triumph for a documentary.
Yeah, and in petrophysics, the pore system is the genre of the rock.
The pore system.
Right. It physically shapes the final result of any tool response you get. When we talk about the pore system, we're looking at the geometric reality of the rock matrix.
So the actual physical space.
Yeah, exactly. If you visualize a handful of coarse sand, the grains are irregular, right? They don't interlock perfectly like puzzle pieces.
There's always little gaps.
Exactly. That interstitial void, the empty space between those solid mineral grains, that is the pore space. And in a subsurface reservoir, that space is under immense pressure and filled with fluid.
Which could be saline water, liquid hydrocarbons, or gas.
Oh, got it.
And the sources really drive this home. The physical packing of those grains and the fluids trapped between them, that is what gives the entire downhole interpretation its meaning.
Because every signal bounced down a wellbore is just, well, it's an interaction with that specific geometry.
Right, which pushes us into how we actually verify that geometry when it's, 3 miles underground. The source establishes a traceability framework for this.
4 specific interpretation controls.
Yeah, 4 controls designed to keep the analysis tethered to reality.
Because traceability just means maintaining an unbroken chain of evidence. If you make a claim about, say, reservoir deliverability, you must have a traceable path backward through the data.
Right, you can't just guess. And the text breaks this down into 4 controlling steps and assigns them cascading percentages of certainty, which I found fascinating.
It's a really useful metric.
So starting with define rock at 92%. Second is measure properties at 84%. Third is check fluids at 76%. And the fourth control is review assumptions at 68%.
Right, they cascade down.
Here's where it gets really interesting. I actually want to push back on these descending percentages a bit.
Okay, let's hear it.
We go from a 92% certainty all the way down to 68%. Does this imply that establishing the rock context is, like, the only thing we can be truly confident in? Because by the time we reach our assumptions, it feels like our workflow is essentially bleeding certainty. If our assumptions only carry a 68% traceability weight, aren't we building a massive economic decision on a surprisingly shaky foundation?
Well, so the descending traceability isn't suggesting that the later steps are inherently flawed or that your foundation is crumbling.
Okay.
It illustrates the cascading nature of empirical certainty. We're moving from fundamental physical realities to dynamic interpreted conditions. Let's look at the mechanics behind each control.
Let's do it.
Defining the rock sits at 92% because it's the baseline physical truth of the system. This is your lithology, your depositional environment.
Like figuring out what we're actually looking at.
Exactly. Is it a high-energy Aeolian sandstone, or is it a low-energy marine shale? Because if you misidentify a carbonate formation as a clastic sandstone, well,
The software will still give you an answer.
oh yeah, every single porosity and saturation calculation that follows will be mathematically executed by your software perfectly, but it'll be physically impossible.
Wow. Okay, so the 92% represents the structural reality that governs everything else.
Exactly.
So once the baseline rock is locked in, we step down to measure properties at 84%. This is where we're dealing with porosity, the volume of that empty space.
Right, and permeability, which is how easily fluid can actually flow through those interconnected pores.
So why the drop to 84%?
Because we're transitioning from identifying a solid physical object to quantifying its microscopic properties using remote sensing tools, and, every tool has a resolution limit.
Sure, they aren't perfect.
And every logging run has environmental corrections you have to make. Borehole size, drilling mud invasion, temperature gradients, there's a lot of noise.
So we're no longer just asking, what is it? We're asking exactly how much space is inside it.
Right, and that introduces mathematical translation and, naturally, a margin of error.
That makes sense. Which makes the drop to 76% for check fluids entirely logical, I think, because now we're dealing with the actual contents of that microscopic space.
And fluids in a reservoir are highly dynamic. They are not static at all.
Because they're reacting to the extremes of the subsurface rock.
Constantly reacting. A fluid's pressure, volume, and temperature, its PVT properties, they change drastically depending on depth.
Like how drastic are we talking?
Well, like a hydrocarbon might exist as a liquid at 10,000 feet under immense pressure. But as it moves up the wellbore, the pressure drops, and it flashes into a gas.
Oh, wow. So you're dealing with a moving target.
Literally. You're trying to pin down the behavior of saline water, heavy oil, or volatile gas in an environment that is constantly exerting varying thermal and mechanical stresses on it.
So the certainty is lower because fluids are just inherently elusive compared to the solid rock matrix.
Exactly.
Which brings us to the final control, review assumptions, at 68%. This is the lowest confidence tier.
Yeah.
But arguably the step that saves you from publishing a disastrous report.
It really is. It forces you to construct a boundary around your ignorance.
I love that phrasing, constructing a boundary around your ignorance.
Because petrophysics is, at its core, a discipline of incomplete data. We never have a perfect, high-resolution picture of the entire reservoir. We just don't.
Right. We're basically interpolating between tiny pinholes in the ground.
Yeah. We extrapolate between wells. We make assumptions about water salinity. We assume the borehole didn't collapse during logging.
And reviewing those assumptions at the end of the workflow dictates exactly what your interpretation can and cannot claim.
It sits at 68% because assumptions are basically the theoretical glue holding the empirical data together.
So they interlock. The 92% certainty of your rock definition is the structural support for the 68% uncertainty of your assumptions.
That is the crucial takeaway for anyone implementing this. If that initial rock definition is weak, the entire cascading chain fails.
And that strict requirement to lock in the physical context That brings us to the dark side of petrophysics, doesn't it?
Uh-oh.
When beginners face the immense complexity of these cascading variables, they tend to look for a shortcut.
Yeah. What's fascinating here is how universal this shortcut really is.
Human psychology at work.
Totally. Human psychology craves a definitive, uncomplicated answer, especially when a multi-million-dollar decision is looming over your head.
And the source material actually labels this the trap.
The trap. The beginners constantly attempt to collapse this really nuanced four-step workflow into a single number output.
They just want the answer.
Right. They run a quick, deterministic equation on a software platform and declare the porosity is precisely 15%.
Without ever defining the rock or checking the fluids.
Yes. And the text provides an aggressive warning against this. Do not let one number carry the interpretation.
Because a single number feels actionable to management, right? It feels like a solved puzzle.
It's comforting, yeah, but it's dangerous.
But the workflow requires you to apply what the source calls the check. You have to restrict your technical claims strictly to what the evidence can support.
And before an interpretation is finalized, it must be cross-examined against two distinct categories of subsurface evidence.
The text refers to these as the two windows into the subsurface.
Yeah, because we can't physically travel 3 miles underground to inspect the reservoir, we rely on these windows. The first is direct evidence.
So tangible reality.
Exactly. Physical truth, completely separated from downhole wireline interpretation. If you drill into the formation, cut a physical cylinder of rock, and pull that core sample up to the surface, you have direct evidence.
You can actually hold it in your hand.
You can place it in a laboratory, run fluids through it, measure its grain density, look at the pore throats under an electron microscope.
So direct evidence anchors the reality.
Mm.
If a software model says the rock has 20% porosity, but the physical core sample on your desk only has 8%.
The core wins. Every single time, the software model is wrong.
Which leads to the second window, interpreted evidence. This is where we send wireline tools down the wellbore to measure physical responses and infer the rock properties.
Right, and this relies heavily on specific well logs, your gamma ray, density, neutron porosity, resistivity, and sonic logs.
Let's break those down, because interpreted evidence is where you really have to marry the physics of the tool to the geology of the rock.
Let's take the gamma ray log, the GR. It measures natural radioactivity. Shales and clays contain radioactive isotopes like potassium, uranium, and thorium.
But clean sandstones and carbonates typically do not.
Exactly.
Yeah.
So the GR log plugs directly into our 92% define rock control. By measuring the passive radiation, we can differentiate the reservoir rock from the non-reservoir mudstones.
Establishing our geological baseline.
Boom. Step 1, done.
But the gamma ray doesn't tell us about the pore space. For the 84% measure properties control, we have to actively bombard the rock. Right. We use the density and neutron logs, DN and NPHI.
This requires understanding the downhole physics. The density tool emits gamma rays into the formation and measures how they scatter back.
A process called Compton scattering, right?
Yeah, Compton scattering. The gamma rays collide with the electrons in the rock. A dense rock with very little pore space has a high electron density, so more gamma rays scatter back to the detector.
Giving us the bulk density of the formation.
Yeah.
And the neutron tool runs alongside it, but it uses completely different physics. It shoots high-energy neutrons into the rock.
Right, and neutrons have a mass almost identical to a hydrogen nucleus. So when the tool fires fast neutrons into the formation, they collide with various atoms. But because of the matched mass, they lose the most energy when they hit hydrogen.
Oh, like a billiard ball hitting another billiard ball dead on.
That is the perfect analogy. And since hydrogen is a primary component of both water and hydrocarbons.
But generally absent in the solid rock matrix itself.
Exactly. The neutron log is essentially a hydrogen detector. It measures the fluid-filled pore space. By running density and neutron logs together, you get a highly accurate measurement of the physical voids in the rock.
Which isolates the geometry. But it still doesn't tell us what specific fluid is trapped inside those voids.
Nope, that's the next step.
So to check the fluids, our 76% control. We look at the resistivity log, the RES. And I really like to think about resistivity like trying to run a marathon through different materials.
Oh, I like this. Go on.
If you try to run a marathon through a swimming pool, the water just moves around you easily. Formation water, deep underground, is highly saline. It contains dissolved salts, which makes it incredibly conductive.
Very conductive.
So if we shoot an electrical current through the rock, it flows effortlessly through the water. The rock has low resistivity.
But if you try to run that same marathon through, say, a giant ball pit,
You're going to strike.
you're barely going to move. And hydrocarbons, oil and gas, they are electrical insulators. They do not conduct electricity.
Right.
So when you pass a current through a rock whose pore space is filled with oil, the current struggles to pass. The resistivity spikes dramatically.
So the RES log directly answers our fluid question by mapping the contrast between conductive salt water and resistive hydrocarbons.
Exactly. Swimming pool versus ball pit.
And finally, we have the sonic log, SON, which measures the acoustic transit time, literally how fast a sound wave travels through the formation.
Right, because sound moves faster through a solid, rigid mineral matrix than it does through fluid-filled pores.
So the sonic log helps us understand the mechanical elasticity of the rock, further refining our porosity models. Every single acronym on that log header represents a physical interaction with the subsurface reality.
It's all connected.
So what does this all mean? We have the 4 cascading controls, the 2 windows of evidence, and the physics of the wireline logs. How do we take this massive theoretical framework and turn it into a practical, actionable sequence?
Like for a petrophysicist sitting at their desk right now?
Exactly, staring at a new data set. What do?
Well, it requires abandoning the checklist mentality and adopting a disciplined narrative sequence.
Okay.
When you are tasked with interpreting a new zone, your immediate goal is to answer one question. What evidence supports this interpretation?
So you don't start by looking at the porosity curve.
No. You start by framing your analysis entirely around the defined rock control. You look at the gamma ray, you look at any available core data, and you establish the geological environment.
You lock in the genre of the rock.
Lock in the genre. Once that baseline is established, then you layer in the logs. But you use the density, neutron, and resistivity logs as supporting corroboration, not as absolute truth.
You're using them to check your work, essentially.
Precisely. You take the porosity and fluid saturation calculations, and you stress test them against your rock definition.
Right, so if the density neutron cross plot suggests a 25% porosity, but your gamma ray and core data show a tightly compacted, heavily cemented shale.
You have a major conflict. The physical rock does not support the mathematical interpretation.
And the rock always wins.
Always. You use the tools to build a comprehensive case, constantly cross-referencing the logs against the physical reality.
And you close that review path by bounding your assumptions. You explicitly state what you are inferring, right?
Yeah, you write it down. I am assuming a water salinity of 50,000 parts per million based on an offset well. Or I'm assuming the borehole was completely stable during logging.
By stating the assumptions, you aren't weakening your interpretation. You are defining its exact operational limits.
Exactly. The ultimate takeaway from Chapter 1 is really a two-part harmony. Understand the rock, then interpret the data.
In that order.
In that order. The objective of this beginner workflow is not to memorize the Archie equation or to learn how to, click the right buttons in your interpretation software.
Right.
The objective is to build a reflexive habit of anchoring every mathematical output to direct source evidence and physical context. If you master that sequence, you evolve from someone who merely calculates numbers into someone who actually translates the subsurface.
Translates the subsurface. I love that. So for you listening right now, dealing with these massive data sets, we highly recommend integrating this sequential review path into your daily routine.
It will save you from some very expensive mistakes.
Do not let the pressure for a fast answer push you into the single number trap. The next time you pull up a log and look at the resistivity and gamma ray curves, remember that those lines are just echoes of a physical architecture. Focus on the rock first.
And as you think about that physical architecture, I actually want to leave you with a scenario to consider.
Ooh, all right.
We explored how the entire sequence of interpretation, the cascading certainty we talked about, is heavily controlled by our initial definition of the rock, that 92% baseline.
Right. It's the foundation.
Right. So if the foundation dictates everything that follows, what happens to the billions of dollars invested on confident, single-number answers when an industry suddenly discovers that a basin's fundamental geological context was completely misunderstood from the very start?
Oh, man. That is a terrifying and fascinating question to end on. Thanks for listening to Petrophysics Daily. See you in the next chapter.